All right, so welcome back to the Water Resources and Environmental Engineering review. Today we're going to be looking at water distribution systems, and I have a few practice problems for you all. And if you didn't check out some of the previous videos for water resources and water engineering, then you can check those videos out. We're currently on part D, but in the previous videos we went through your basic hydrology, your basic hydraulics. We went through pumps, and now we're currently on water distribution systems. All right, so let's go ahead and dive right in. Number one says calculate the head loss in a 300-meter length of pipe with a diameter 200 millimeters, given a flow rate of 0.02 meters cubed per second and a Darcy Weisbach friction factor of 0.025. Okay. So what information are we given to start? Well, we are definitely given a lot of information. So we got length and diameter of the pipe. Okay. We also have a friction factor, which is the Darcy Weisbach friction factor. And then we are given a flow rate. And they want us to find the head loss. I'm assuming due to flow. So I don't know what this Darcy whatever, but I'm assuming it's important. So I'm gonna go to Darcy. I'm afraid if I try to spell that. Let's just look up Darcy to start. Head loss due to flow. I feel like we saw a similar problem in one of the previous examples, but let's check out the information that we're given. So we are given Darcy or Stanton friction factor. We have that, which is F. Do we have L? We're given the length, 300 meters. Diameter, which is D. We're not given V. And we know what G is, which is 9.81 meters per second, or gravity, right? So how do we get, so it looks like we don't have H of F and we don't have V. Can we get V? Well, I know we have Q and we have the cross-sectional area, A. So there's a formula that's pretty important. Where if you're looking at a one-dimensional flow, Q is equal to, or volumetric flow rate is equal to A, cross-sectional area of flow. So if I have this pipe, right, and there is flow coming up the pipe, down the pipe, wherever through the pipe, then A is the cross-sectional area of this circle here. And so we're given that diameter, right? That diameter is equal to 200 millimeters. So how do we get A of a circle, right? Or that cross-sectional area? We would just say, so we'll write out top Q is equal to A times V. We have Q. So Q is equal to 0.02 meters cubed per second. A is equal to, well, what's the area of a circle? Pi r squared. And we want to keep everything in meters. So what is R? R is equal to diameter divided by 2, right? 200 millimeters divided by 2 equals 100 millimeters, or 0.1 meters, right? So A is equal to pi times 0.1 squared, which equals to 0.0314 meters squared. Okay, so we now have A and we have Q. All right. So how do we get V? Well, Q is equal to A times V. Q is 0.02 meters cubed per second, which is equal to 0. So it's equal to A, which is 0.00314 meters squared. Where am I getting that number from? Here. Okay. And then times V. All right. So when you divide both sides, you get V to equal 0.636 meters per second. Okay. So we have V. All right. So let's go back to our, so here we can erase and say we know what V is. All right. So H of F, which is head loss, it's the only thing we don't know. All right. Let's see if we can get back to that equation of head loss due to flow. Yep, it's the Darcy back equation. So we'll write it out and we will get our answer. So HF is equal to, what's the first component? F. What is F? F is going to be equal to the friction factor, or 0.025. Okay. Times 300 meters. Why did I say 300 meters? Well, that's the length of the pipe, L, over D. What is D? It's 200 millimeters, but we want everything to be in meters, so it would be 0.2 meters, right? Times, I know that I got V squared, so what's V? Well, it's 0.636 meters per second. We want to square that and then divide it by, should be 2 times 9.81 meters per second squared. All right, and when we total all that up, we get head loss due to flow is equal to 0.77 meters, or A. All right, let's look at number 2. All right, so determine the required volume in gallons per minute for an elevated reservoir in a water distribution system serving a population of 10,000 people with a daily demand of 200 liters per person. A lot of information. What information are we given? We are given the population, right? What is the population? It's just the amount of people in this specific area, right? Which is going to be 10,000 people. So we need enough water to serve 10,000 people. So we got population, we're given, and a daily demand, right? And so if you have, I'm just going to draw some Johnnies, and you got Bob, and you got James, and you got Paul, and you got Baker, and you got Daniel. You get the point. And so this is a total of 10,000 people, right? I could keep drawing Johnny Cash, Johnny Depp, right? So this whole circle of people, let's just call it 10,000 people, right? 10,000 people. Try to highlight. Okay. So these 10,000 people all need water, right? They all need water. Let's draw this little bucket. Water. And when it comes out, so each person, when they hop out their bed, let's say they're hopping out. So James, he hops out, he gets in the shower, right? He needs some of this water. He demands 200 liters of water, right? And then you got all these people jumping out, all right, getting up. And so then you got Daniel, he jumps out, and he demands 200 liters. And this is daily, right? So this is what this problem means, right? So just wanted to give you a little visual. I like to draw sometimes that you can see what's going on. All right, so how do we find the required volume? In gallons per minute. Okay. All right. So this to me, I think is going to be a unit conversion problem. All right. If I have, let's use green. I have 10,000 people per day. Right. And each day, $200 liters go to one person, right? All right. And so I need this unit to end in gallons and minutes. So I currently have units, right? If persons are done and those units cancel, all right, I know that that's going to give me my answer in liters per day. Those are the only answers that are still, or the units that are still available, right? So how do I go from liters to gallons? Easy. I'm glad you. So we would go to unit conversions, right? In our handbook. I don't know how many gallons and liters this stuff is. Okay. I can find out. So if I look at gallons, all right, I know in 1 gallon, there are 3.785 liters. Right. So I'll write that. 1 gallon. It's going to be 3.785 liters. All right, so now we have it in gallons per day. All right, because our liters now cancel out in units. And we can solve for how many gallons per day we need. We need gallons per minute. So break this up. We can break it up into, we can go from days to hours to minutes, right? So how many hours are in a day? So 1 day equals 24 hours. How many minutes are in an hour? 1 hour equals to 60 minutes. And so we cancel all these units. Hours cancel, days finally cancel, and we're left with gallons per minute. And so we multiply all these values out. Let me highlight the values that I'm talking about. So we need the 60, we need the 24, we need the 1, right? We need the 3.785, we need the 1, we need the 200, and we cannot forget about the 10,000. Okay. So if it's on top, you're multiplying. If it's on bottom, you're dividing. Okay. All right. So this total, when I multiply and divide everything out, I get 366.94 gallons per minute. And we can just round that up to 367 gallons per minute. So answer is C. Alrighty, let's look at number 3. This one says, in a water distribution system, water is flowing through a pipe with a diameter of 150 millimeters. If the flow velocity is 1.5 meters per second, calculate the flow rate. Okay. So we are given diameter pipe. This is boring. Let's make it red. And we're given the velocity of this flow going through a pipe. Then what is our flow rate? So find flow rate. And it looks like our flow rate needs to be in meters cubed per second, because that's what our answers are all in, right? So what are the formulas that we need? Flow rate given diameter, we're given a velocity. We've done some like this. Flow rate. Okay, so fluid flow. That's pretty important. You know, it needs to be fluid flow. So volumetric flow rate is Q. So we don't know that, so we're trying to calculate. Do we have A? We know the diameter. So if we have the diameter of the pipe, then we can get the cross-sectional area, which is what it is. Okay, and then we have V. So our equation that we'll need is Q is equal to A times V. Okay. What is A? A is equal to cross-sectional area. This is a pipe, circular pipe with the diameter of, it's a circle, right? So what's the area of a circle? Pi r squared. What is r? R is equal to the radius, or 150 divided by 2. This is your diameter divided by 2. Right, that's millimeters. So R is equal to 75 millimeters. Or if you want to go from millimeters to meters, then we would do 0.075 meters, right? Okay. So what's next? We now know R. So now we need to finish solving A. A is equal to pi times R, which is 0.075 meters. Square that. So for A, you should get 0.0176 meters squared. Okay. Now we're not done. We got our A. Do we know what? So we have A. Do we know what V is? V is equal to 1.5 meters per second. We're given the velocity, right? So now Q is equal to A 0.0176 meters squared times 1.5 meters per second. When you multiply that out, you should get 0.026, and your units of meters squared plus, or a meter squared times a meter is a meter cubed divided by S. All right. So we know that our units are correct. And we get A for this one. All right, so this concludes the water distribution systems section. Next section, we're going to be looking at flood control, dams, routing, runoff, bunch of stuff. So I look forward to seeing you in the next video.